All right, good morning, everyone. Not keeping in line with French tradition of starting 15 minutes late. We're going to start on time at 30, so welcome, everyone. I'd like to officially welcome you to the 2023 Shannon Lecture that will be delivered by our 2023 Shannon Award winner, Professor Rüdiger Urbanke. Professor Urbanke obtained his diploma engineer degree from the Vienna Institute of Technology in Austria in 1990, his master and PhD degree in electrical engineering from Washington University in St. Louis, Missouri in 1992 and 1995, respectively. He's held a position at the Mathematics Communication Department at Bell Labs from 1995 until 1999, before becoming a faculty member at the École Polytechnique Fédérale de Lausanne, EPFL, where he's still today, and he's currently serving as the Dean of the School of Computer and Communication Sciences. So his main research interests, as some of you might know, have been on the analysis and design of error control coding schemes that allow reliable transmission close to theoretical limit and at low complexity. I think these error control codes are now part of most modern communication standards, including wireless, optical communications, and hard disk storage. So if you are using a 5G connection right now, you're most likely using LDPC codes whose design was influenced by some of his early work on multi-edge type LDPC codes. I think more broadly, his research has focused on the analysis of graphical models and the application of methods from statistical physics to problems in communication. He's the co-author of the book Modern Coding Theory that was published by Cambridge University Press, which shortly after his publication very quickly became the reference in the field. He's also the co-recipient of several IT Transactions Paper Awards. He received it in 2002, in 2013, and in 2021, making it, I think, the current standing record, if I'm not mistaken. But I think beyond the numbers, I think if you look at that sequence, it's really a testimony to his dedication to solving one, if not the earliest and most fundamental problem posed by Shannon in information theory. How do we design actual error control codes with low complexity that would achieve capacity? And I think this sequence of awards is a testimony to his laser focus on solving this single most fundamental problem. Professor Urbanke has also received numerous other accolades for his work over the years, including the 2011 IEEE Koji Kobayashi Award, the 2014 IEEE Hamming Medal, and the 2016 Stock-Based Paper Award. So I'd like to add a more personal touch to this introduction. Back almost 20 years ago when I started my PhD, I first walked in the office of my advisor, and I said, yeah, I'm interested in information theory and coding. And he, looks at his desk. Back then, we still had papers and come-ups with a thick green issue of the Transactions. So for those of you old enough, that's a 2001 special issue on codes. And he tells me, this is full of gems. You should read it. And I do believe that the first paper I read was Rudy's paper on the capacity of message passing decoders. And I do remember spending, in the pre-GitHub and Facebook era, spending quite a few hours trying to code density evolution in C. No one does C anymore. Trying to track memory leakage because of wrong mallocs, trying to make an FFT work. And I think, while Rudy's achievement early on, I think were already an accurate predictor of his future career, I don't think I could have imagined that 20 years later I'd be here standing, having the honor of introducing him. So the Shannon Award, really celebrates and recognizes consistent and profound contributions to the field of information theory. But I think stopping here would not do full justice to everything Rudy has done for our community. I think he has devoted much time and effort in service of our community, starting by serving as an associate editor for the Transactions in the early 2000s, becoming an elected member of the BOG in 2013, and serving as our IT Society president in 2017. In addition, again, for those of you who are old enough to remember, you might remember that in the mid-2000s, if you wanted to find a good degree distribution for LDPC code, you would go on the internet, Google good degree distributions, and you would be linked to a website, which I think has unfortunately disappeared in the archives of the internet, called lthc.org. And you would have access to the results of hundreds of optimization of thresholds and degree distributions for LDPC codes. You could also run your own optimizations if you wanted to. And I think that became, I think, a de facto repository and a good resource for countless of young PhD students like myself. So beyond, his contributions, in service of our society and leadership roles, I think his decompression sessions at the Information Theory and Application Workshop really quickly became, if you've had the chance to attend some of these, a very anticipated event that really contributed to building a community of collegiality and friendly interactions. And I do remember a few years, maybe it was mid-2010s, Rudy was talking to me and he said, I'm getting slightly worried. I just ran into a student in the hallways, and the student approached me and said, "Oh, you are Rüdiger Urbanke." And Rudy thought, okay, somebody has read my books and my papers. And the student said, "You're the entertainment guy." So, in hindsight, I think you would agree with me that Rudy's concern for being remembered as the entertainment guy were somewhat unwarranted. And without any further delay, it is my great honor and pleasure to yield the stage to Professor Urbanke.
Thank you so much, Mathieu, for this most kind introduction. Talking about kind, it's amazing to be in Taiwan. I don't think Switzerland is a particular rude country, but the level of kindness and helpfulness is just off the scale here. So it's fantastic to be here. It's also a fantastic opportunity to talk here in front of the ISIT community, which is really my intellectual home for the last 30 years. Now, everyone told me a year ago that this talk would ruin 1 year of my life, okay? I'm not sure it's good to say, but I'm happy to report it didn't, okay? And I have high hopes for technology, so when it came finally time to prepare, I fired up ChatGPT, and I said, give me a talk outline, okay? And I didn't just want to have any talk outline, I wanted to have something nice. So it said, make it as short as Alon Olitsky's China talk, okay? And boom, okay, it didn't disappoint, okay? And who am I to argue with ChatGPT? So that's what we're gonna do, okay? Now, one thing I don't want is that when you go out and someone asks you, how was the talk, okay? You'll say, well, there were a lot of question marks, okay? So let me decode it for you. I don't know about you, but at least for me, right? I'm constantly in a state of confusion, blocked, don't know how to continue. But fortunately, there are many sources of inspiration, and we had heard on Monday, about statistical physics, and on Tuesday about math, and yesterday Amir put it both together, right? And so, some of them are of this form, right? Let me add information theory, it has great idea, or computer science. But at least for me, at least as important, and I hope I will be able to convey that, has been luck and serendipity, okay? This has not been, contrary to what we write in our grant proposals, this has not been a 10-year plan, okay? Has been a meandering walk of everything. So as you use them, hopefully some of these things will get resolved using these techniques, and even so, it might still be that there will be some things will simply be too ambiguous, and for me at least, I think that's okay. Right? So as you wonder about a problem, as you're walking around and wandering around, you might freely borrow from other fields or steal ideas. Sometimes it's okay to just directly take them and adopt them. Sometimes you have to adapt, okay? And hopefully you make progress and then you start all over again. At least that has been my experience. Now, people say that everyone remembers the day when JFK was shot. I don't, because I was -3 years old, okay? But I do remember the day the French Revolution started, okay? And so when the French Revolution started, it was super exciting, okay? I just immediately knew this was exciting. I didn't know what I would do or what I could contribute at, but I immediately knew that I wanted to be part of it. And it was also immediately clear to me that I'd much rather be like the guy on the left than the guy on the right, okay? And so, that was the beginning of the journey. And so I think fitting to the theme of the talk is that when Perot, Clavier, and Titmaschine started turbo codes, they didn't set out to revolutionize coding theory. They were interested in hardware, trying to build better codes in hardware, and they were inspired by something very concrete, right? Something outside their field, turbo codes, and the rest is history. Now, very early on, the tone was set by this set of people, Benedetto, Mondorsi, Diffsala, and Pulara, and they, invented something which is called the uniform interleaver, which led to something very similar to what Neri was talking, an ensemble, analysis of turbo codes, in particular about the weight distribution. And just a small side remark, if you ever cite a paper and the paper has, let's say, 3 authors, maybe 2, okay, don't write Benedetto and al, okay? Poor Guido, for many years was just known as Mr. El Al, okay? Not nice, okay? Now, so that started the theme, and this continued for a few years. People then looked at not just the ensemble average, but what's the worst case, best case, how things can actually grow, and so that was quite important. The interleaver design, many interesting things, of course, and a ton of applications, and I could have picked hundreds of names in here and hundreds of applications. So I'll just flash them fast enough so that we can all pretend your paper wasn't there, okay, if I inadvertently forgot it. Good, so this was quite exciting. Turbo codes, weight distribution, early days. And I'm gonna come now to by far the most complicated part of the story. In fact, it's so complicated. I think the only thing that's more complicated is trying to find a perfect match, okay? And so I don't think that it is humanly possible to disambiguate all the threads that led to this evolution. But I was told early on that you should never, ever apologize in a talk. You should just blame someone, okay? And I'll blame all these brilliant researchers that you find on there, and the many ones that I couldn't even fit on there, for coming up with a flurry of ideas in a very complicated history that you couldn't possibly do justice to. Let me nevertheless try. Now, very soon after the discovery of turbo codes, as revolutionary as they were, people discovered that pretty much everything had been done by Gallagher beforehand, right? In a different form, in a different language, but it was so much ahead of the time that really it was basically forgotten, except for a few heroes like Michael Tanner, who particularly invented the language that we use here, and in particular this graphical description. Every linear code has a parity check matrix, and this is the bipartite graph that represents it. These are the variables, these are the checks, and so these are the edges. So these are the checks that this variable participates in. These are the checks, and the edges point to the variables that this check checks. And the only important thing for low density, this exists for everything, is that you have a small number that doesn't, of these edges, and this, there might just be a fixed, then it's called regular, for example, a 3-6 code. Every variable has degree 3, every check has degree 6, or there could be variable, but it's a fixed number that doesn't grow with n. So that will become important. Now, soon, after discovery of turbo codes, particularly, McKay and Neal came in, and they had, rediscovered Gallagher's work, improved it, found better codes, and repopularized them. And, physicists are no slouch either, so they came in very early on. In particular, actually in '89, it was Sirlas who had looked, this is before turbo codes, which is '93, and had looked at basically, again, these type of codes without knowing anything about Gallagher or anyone else. Unfortunately, he picked low-density generator matrix codes, which are kind of the dual. If by some chance he had picked low-density pair check codes, he would have been the leader of the French Revolution. okay, which is again with my theme that there's a lot of things that are quite random. But because he picked low-density generator codes, which later on became very popular as ratelet codes, but by themselves weren't that good, and maybe also because he published it in the kind of physics-related journal, it didn't really catch fire. But as soon as turbo codes came out, he got back into the game. In particular, he paired up with Andrea Montanari, whom we'll see several times. Many other people, Nicholas played a role, David Saad, Kabashima, Vincente, Maruyama, Ido Kanter, etc. Now, if you have ever seen a paper in statistical physics, and you're not from this area, you know it's not easy late night reading, okay? And so for most of us who first saw them, we simply said, what on earth are they talking about, okay? And so it took quite a while for these amazing results to actually enter into the consciousness of the community. Now, perhaps the most influential set of works came from computer scientists. And again, they didn't know anything about Gallagher, and they didn't know anything about turbo codes. They were motivated by content distribution, which was quite an important topic at that point, and had previously looked at Reed-Solomon type constructions, and essentially on their own reinvented everything. And for content distribution, it's really the erasure channel that's important. So they really focused on the erasure channel, but for that channel, they came up with a complete analysis, perfect, the optimum codes, etc. And I'll get back to this in a time. So let me just mention Sipser, Spielmann, Luby, Mitzenmacher, Chocolai, and Steeman should also be somewhere around. Good. Science often evolves by bursts or flurry of ideas, which make things seemingly complicated, and then things again collapse by people coming around and unifying them. And one of these unifications happened with the work of Wieberg, and then Löhlinger and Kötter, and Frank Chichen was also in there, in which they realized that all these notions that people had come up with in completely independent communities that didn't even talk most of the time together, things like turbo decoding, message passing, the belief propagation. We heard Amir, talk about pearls and Bethe, and then there's also the idea of Perl, which is also there, which we should have mentioned, Viterbi and BCGR. They were really all the same things, and there was a uniform language which made things very nice, and the uniform language is the one of factor graphs and the sum product algorithm. A very important conceptual contribution that made all these notions come to life together. Now, let me just quickly explain what this set of computer science did, but let me explain it in the language of yet another thread, and that's Stefan ten Brink, who had invented what he called exit charts, right? And let me do everything in the binary erasure channel where things are much easier. So remember, we have these two sides, the variables and the checks, and you can think of a variable together with the edges as a repetition code, and you can think of a check together with its edges as a single parity check code. And now you can describe for each of these sides, okay, how the input-output behavior is. So think of that there's erasure probably on the edges, there's some processing going on, belief propagation, there's things going back, okay? So there's a number going in, the erasure probably going in, erasure probably going out, and this can be described by a single function as we have this function here for each of these two sides. Now, for Stephen ten Brink, he didn't look actually at the erasure channel, he looked at Gaussian channels, and that's not a real exact description, but one of the realizations that came on at some point was that at least for the erasure channel, all these descriptions are the same, and that's actually exact. And so that's why I want to use this language. And so once you have that, so this is the input-output relationship at the parity, at the check node, at the repetition code, the variable nodes. And now you can call them the exit curves, extrinsic input-output transfer functions. And so now you can think of the actually decoding behavior as an iterative process, processing, messages passed, processing, messages passed, etc. And that exactly corresponds to these steps. And just the way things are set up here is where you want to converge to successful decoding is here the 0.11. Now, as it turns out, right, at the variable node, you don't just have the repetitions, but you also have the observation, and the observation depends on the noise that the channel has. And so this curve is not actually a constant curve, but depends, this point depends on the channel parameter. And if it just happened to have the channel parameter a little bit more noisy in this description, then it would happen that decoding wouldn't converge because it would get stuck in one of these fixed points, right? And so now, as I said, computer scientists in entirely different language using an entirely different decoding algorithm, but equivalent, which they called the appealing decoder, and a method called the warm-up method, figured out that that was an accurate description. And so now you have a very nice graphical description in this 10-brink thing. You just want these curves not to overlap. Okay, so very nice. Now, one other important thing that we need is the area theorem. Stephen de Brink very early on had already kind of looked at that. He had played around with Gaussian channels and computed what the area under such curves are. And he had figured out they roughly have to do with the rate. And he was then, together with Alexa Schickmin and Gerhard Kramer, that they put, for the erasure channel, they proved indeed that's exactly equal to the rate. So what turns out is that the area below here is just equal to the rate, which just happens r minus 1 over r, or 1 minus 1 over r. And on the variable node side, it's a little bit more complicated because just so that things fit together, we're not actually plotting the exit curve, but the inverse, and there's also the channel parameter. But if you do a little bit of math, you will say that it's epsilon, the channel parameter, divided by L, which is the variable, which is the degree here. And why was that important? It's important because if you don't want these curves to overlap, a trivial bound is the following, right? The whole area is 1. This area is 1 over epsilon. This area is 1 minus 1 over r. If they don't overlap, okay, must be that 1 must be bigger than the sum of these two areas, right? That's obvious. And now if you slightly rewrite that, and then we identify what these things mean, then this equation tells us that on the left you have the rate of the code, 1 minus L over r. On the right we see the capacity of the erasure channel, right? And okay, that's not an amazing statement. Okay, the rate for successful decoding has to be less than capacity. Okay, fine. But the nice thing is that we can actually take this literally and turn it around and see if we actually want to achieve capacity. Basically what we have to do is we have to get this to be 0. This means we have to match these curves. And that led to this observation of the matching condition, right? So if you manage to get these curves to match and have essentially 0 error, you achieve capacity. And all this was done in an entirely different language, entirely different methods by the set of computer scientists. And I'm just quoting one particular degree distribution that does it. But you can see there are many other ones that they had already found out. So this was a big important step in trying to understand what was happening. And for us, we'll need a slightly different picture. So what is an exit curve? You take a component code, you look at the input erasure probability, you do the processing, you look at the output, right? Now you cannot just do this for this component, but you can also do this for the overall code, right? So take the overall code and look how it behaves. And you will see now in the future a lot of pictures like this. Again, the erasure probability, input erasure, something like the erasure probability at the output. And now do the following experiment. You pick a certain erasure probability at the input. You run, let's say, this belief propagation algorithm forever. And if the channel is very noisy, you won't be able to decode. Depending on the code, you will get stuck somewhere. Mark this point. But if you pick a code, you pick a channel parameter that's good enough, you probably will be able to decode. Do this for all the parameters you have, and you get a typical curve like this. And since this is the decoder that the belief propagation decoder, let's call it the BP exit curve, right? So you'll see pictures like this. Okay, so we have a fairly clear understanding now what it takes for the erasure channel to get close to capacity and made quite some progress. What about, channels? Well, in channels, we need slightly more sophisticated notions, in particular dense evolution and Gaussian approximation. If you don't know what Gaussian approximation is, let's ask ChatGPT to give us Gaussian approximation. Okay, I hope that's helpful. Okay, so what you do here for channels, it's not a number that you have in and the number that comes out, but these are densities. Okay, so imagine that these messages that you send are log likelihood ratios. These are real numbers. There will be a distribution of them, and you need to keep track of the distribution. That's the state of the system, okay? Start with a distribution, comes from the channel. You do one iteration, get another one, another one. That's what's called dense evolution. And so, it's very, it's clear to see. And in this particular picture, if these are log likelihood ratios, set things up, you want this density to go to plus infinity. That's successful decoding. And if it's too complicated to compute these densities accurately, then you can replace them by Gaussians or mixtures of Gaussian. And indeed, Se-Young Chang did that, and that's of course then much easier because now you just need to keep track of mean and variance, or maybe a set of them, and that's much faster. And once you have this, of course you can, we heard before, and you can now optimize as to your heart's content and find out what good degree distributions under various conditions. And indeed, Forney used to say this was before AI, where now we are used to trillions of parameters, but he basically, Se-Young basically optimized until the lights dimmed at MIT and found codes that were extremely close to capacity this way. Okay, so this was for channels. Okay, let's make things a little bit more complicated still, okay? And let's look at the following. Let's bring in maybe a little bit physics also. Now, if you ask ChatGPT to give you the best joke it knows about ideal gases, okay? So this is the best joke it can come up, okay? It's not terrible, okay? But I think, we still have a few years, okay, where we can hope to, still have some input, okay, before the overlords take over. Okay, so let's get back. This is the curve. This was under iterative decoding. And now let's ask what would happen if I tried to decode such thing optimally. And in hindsight, you might say, why might you want to do it? Well, in hindsight, you might say that at that point of time, there were hundreds of people trying to find better codes, but there were also lots of people that trying to come up with better decoding algorithms. And in order to know where you should focus on, you should maybe understand, is it the fault of the coder or the fault of the decoder that we perhaps don't get to capacity? Okay, that's of course now happened. Okay, the reason that we looked at that was simply, it's like Mount Everest, it's there, okay? But I think in hindsight that could be a justification. And it turns out you can figure out, and it turns out that basically up to some point it's the same, okay? It doesn't matter. But you can see that the threshold is more to the right, so it can tolerate more noise. And that was done together with Cyril and Andrea Montanari. And it turns out, since this is again an exit curve, but it's under optimum decoding, again, you have an area theorem. So the rate under that will be equal to the rate of decode. Now, perhaps more interesting than just this number is how this comes about, okay? And how does this come about? Well, remember, what is this curve? It's a set of fixed points, and Amir already talked in his talk about it, right? This is fixed points of this dense evolution process. So you start with an erasure, probably you see where it gets stuck. And so these are the fixed points you see. But there are other fixed points in there. These are unstable fixed points, but they exist. And at least for the erasure channel, you can just write down the whole curve. Very easy, right? Now, you never see them because they're unstable. If you started here, you would actually decode to 0, right? But you never get there because you're already being captured here. Now, important about this is that for entirely different reasons, this curve, which is called the extended exit curve for obvious reasons, also has an area theorem associated to it, okay? Nothing to do with optimum decoding, it's just some slightly different proof. And so if you now put these two things together, you will see that one way to construct where this map threshold is, right, where the optimum decoding threshold is because you have these two area theorems, this cut, okay, which is determines where the map threshold is exactly there where you take this kind of fictitious curve here and you cut it such that these two areas are in balance. Okay, so there's a balance between these two areas. And if you see a balance like these areas, and you have ever seen physics, then you immediately know why we call this the Maxwell decoder, or the Maxwell construction. Because when you look at an ideal gas, okay, there was Van der Waal who had, early on when people tried to figure out what's the relationship between the volume and the pressure of an ideal gas, he wrote down a set of equations, and you can write this down in actually a few lines, how they should behave. And he came up with this curve, and this curve, very similar like this, has a non-physical behavior, right? You see it's like this S-shaped curve, right? And of course that doesn't make sense because the pressure, as the volume goes down, the pressure should be monotone, right? And it was Maxwell who then found how to make this physically meaningful by saying that this should be cut exactly at such an area that you have a balance between these two. In his case, it's a balance between either work to be done or work to be gained from the system. In our case, it's a balance between guesses that you have to do, there's a decoder associated to it, and confirmations that it can get out. So it's a balance of two types of information that it can get out. but it's essentially the same type of construction that you have. Okay, so that was for the erasure channel. What about general channels? Considerably more complicated, but essentially the same type of story is true. You know, these kind of fixed point, unstable fixed point constructions, etc. Okay, so all we want to take out from this is the following, that at that point in time, we were able to compute under some technical conditions what were these map thresholds. So for example, for what's called the 3.6 code, the one that I showed you early on, if you go to large systems, you decode them optimally with the erasure channel, you could decode up to a threshold of this, okay? And remember, you should compare this to a half, because a half, it would actually be the capacity given the rate of the code, right? Okay, so now in any good story, first things should get complicated, and at some point, hopefully, things will come together, okay? Let's hope that's the point where they come together, okay? And so these were people that played a role in this. You could maybe call them the ringleaders, okay? And so these are the people that play, we're not talking about spatially coupled codes or convolutional LDPC codes. So how does this story go? Well, early on, people tried all kinds of codes, right? All kinds of constructions. And there were particular Sigangirov, who was a master in convolutional codes. And if you master convolutional codes, everything looks like a convolutional code. So of course, he tried convolutional codes, but for LDPC. So he tried what's called LDPC convolutional codes. And in a language that's slightly different, what you do is you basically take LDPC codes and you put many copies of them in a line, and you somehow connect nearest neighbors, like a picket fence, right? And when you do this, there are many ways to kind of terminate, because it's a line. Either you can do this what's called tail biting, looks like this, or you can do this by terminating. And initially, it was Feldstrom and Sigangirov who tried this kind of codes and then tried to run them, and nothing really interesting happened. And it was later on that set of people, Michael Lendmeyer, Sritan, and there are many papers, again, I just quote one, Sigangirov and Costello, who tried that version. And that version showed a much better behavior than the base code, okay? So they simply string base codes together in that fashion, simulated them, and they worked better. And so, fine, so they worked better. And sometimes in 2009, the following happened. There's this Gianluigi Lever. And some people know 100 digits of pi, okay? I don't know if Gianluigi knows 100 digits of pi, but for whatever reason, he knew at least 3 digits of all these map decoding thresholds, not just this, but many, obviously, okay? And he must have been in a thesis defense. I guess it must have been of Sitaran. And when he talked about, at that point, this set of people had also computed thresholds for these spatially coupled codes, okay? And at the same time, unbeknownst to us and unbeknownst to him, Srini, Tom, and I had discussed, and we came across a preprint of these papers, and we also saw these numbers, okay? And so now let's do I don't know how Gianluigi felt, but I know how we felt, okay? Let's do a dramatic reenactment, okay? These numbers were actually the same, okay? And that's, it's one of these things where you see something interesting must be happening, but it's completely random, right? If Gianluigi hadn't been there, or for whatever reason we hadn't looked at the paper, or maybe the numbers had only been given to 1 digit, nobody might have, realized that, okay? Completely random coincidence. Now, why is that, quite amazing? Is because one is a base code that's decoded suboptimum, optimally, right? And the other one is a construction. It comes from the base code, many copies, and decoded suboptimally, right? And they have the same threshold. Why on earth should that be? And so it took then, for us, it was completely clear what we should be doing. We should be computing at first, just to understand if there's something interesting happen, these curves that I talked to you, these extended, BP exit curves. And indeed, when you see it, remember, that's the map threshold here. As you make this chain longer, you see that these things converge. And if you make it longer, this will converge exactly to this. And why do you need to have longer and longer lengths? Because there's a termination involved. The termination makes the rate smaller. That makes the volume smaller. Remember, there's an air theorem. So in order to really get identity, you would have to go to infinity, right? Otherwise, you get slightly better thresholds. And so, it then took about a year for these two sets of groups to, describe this phenomenon, understand why this actually happened, okay? and published the relevant papers. And then it took even longer to describe how this would happen for channels, where of course things are a little bit more complicated. Fortunately, things didn't just get more complicated. Using potential function, Jedler, Jan Nguyen, and Henry Pfister found an easier version of that proof, which is fairly accessible, and describe why these kind of things happen. Now, of course, as beforehand, once you have some kind of description of phenomena like this, you can apply it to anything you want, right? Just as for all the other examples beforehand. And in particular, it was applied also to compressive sensing, right? And so here's two sets of people. There was Andrea Montanaro before and also looked at that. And why was that important? That was important because this set of people here found a very nice physics interpretation. That's not just an analogy. There's really a mathematical, basically, correspondence between them. This is supercooled water, and I'm sure many of you have seen that. Supercooled water is water that's below 0 degrees, but it's still in water phase, and it's in a metastable phase, so it can stay there for quite a while, has fairly long times. And, but if you give it some bump or give it some boundary condition, it will freeze along this thing. And that's exactly the same phenomena that happens here. And so they explained this relationship. And there's a name related to it that's called nucleation. So there's the nucleus that starts, like in a crystal growth. It starts the solution, and then things will grow. And since it's a one-dimensional structure, it will grow about this one-dimensional structure. And basically, the decoder here that you have is a metastable version of the ground state. And again, we had yesterday heard Amir Demo talk about the ground state. The ground state would be optimum decoding. BP is this metastable state that you see. Okay, we could have all been perfectly happy at that point, okay? And, just play with some more little, improvements. But history had other plans, okay? And what happened, okay? This guy came along, okay? And he said, hold my Raki, okay? And gave us polar codes, okay? And so I think it took him slightly more than 7 days, but still pretty impressive, okay? Now, again, I think it fits very nicely with the theme because Erdal wasn't trying to, as far as I know, revolutionize coding theory. He did what many of us do after 20, 30 years. We go back to our thesis and try to get inspirations, okay? And so that's exactly what he had done for his thesis, right? And so he had worked on this cutoff rate for that. And already Massey had shown that, if you take certain channels, you can split them kind of in two, and the cutoff rate is the maximum rate that you can achieve with a sequential decoder, and it's in general smaller than the capacity they have for the channel. And he had shown Massey already that for certain channels you can split it, and due to the convexity of this cutoff rate, you can do better if you can actually take one channel and split it into two. Okay, the sum of the two will be better. But Erdal found a way to do this with this by also adding a channel combining part, which gave a much richer such sets of ways to split and to combine. And if you do this, and in particular, you manage to get these points to be close to the boundary, then there the two things are the same, and that gave rise to polar codes. Okay, so again, beautiful, but again, a connection that came from just, again, looking back at fundamentals and then coming up with, very, very surprising results. These are the early papers. Of course, Erdal, Emery came into the picture, and Aaron. And then once you know that, again, the sky is the limit. You can use this for source coding. You can try to, use this for any kind of multi-access, secrecy, whatever you want, right? You can apply this. Of course, you can also try to make them better, the exponents, etc. I think very important not to forget is to make them useful was the contribution of Vardy and Ido Tal, who is, I think here, that did list decoding that made it actually something that is competitive. And not to forget all the people who actually worked on implementing it, because it's not enough to have a good idea, you also be able to implement them at the speeds and at the power that is necessary for modern communication systems. And let me just mention, Alex Burg and Warren Gross, and then there are many, many other people who, of course, helped them to get this done. And you have now amazing, efficient implementations. Good. Now, at this point in time, it would have been nice to talk still about the finite length performance. We have now at least two types of codes that achieve capacity, right? And now you might wonder about second order things, so how quickly, what's in the length to do. And one way to do this is, again, something that we heard yesterday about scaling laws. And scaling laws were introduced by this good-looking gentleman, okay, whom we have already seen several times, Andrea Montanari from Bari. We have seen him several times at the Bari Center of many things in coding. And so he came in and showed us how to use something that in statistical physics is very common, scaling laws, and it had a great impact. Unfortunately, I don't have time to talk about it, but fortunately, we heard a glimpse of it yesterday by Amir, how this was used for the binary ratio channel. Now, this would have also been a perfect segue into the final thing of the story. Remember this poor guy, okay? Now, I'm happy to tell you the story ends happily, okay? He's back, okay? And he's back in terms of what's called Reed-Muller codes. So why Reed-Muller codes? Because it was already conjectured for a long time that Reed-Muller codes were actually achieving capacity and even doing so universally. It just took a while to actually prove that. And furthermore, it was conjectured and then later on proved that they would have actually a scaling behavior very close to the optimum scaling behavior, right? Now, fortunately, I don't need to tell you about this story. Some years ago in Hong Kong had the opportunity to tell you about the story that relates to the binary ratio channel, and I'm happy to relay now that Henry and Galen Reeves, but also Colin Sandon and Emmanuel Abbé, found the solution to a very, very complicated problem, namely showing that polar codes are also that Reed-Muller codes are also optimum for general channels. Okay, and so we basically closed the circle, come all the way back, okay, and finished where we started. But now we have essentially optimum codes. There's just one tiny little problem still left. Okay, we don't have a decoder. Okay, just a tiny problem. Okay, so for all of you here who are looking for an open problem, okay, don't pick this one because it's very complicated. Okay, but if someone could find that, or maybe for BCH codes, which it's the same story, that essentially would clinch the deal. Maybe not the only way to do it, but I think that would be fantastic. Okay, so this brings me to the end of my technical part. This was my own little small random walks, and I think I've conveyed to you, kind of how random and was. Now, if you'd ask anyone else in the audience to give a talk about that, they probably would have picked a different walk, and that would have been equally valid. So I hope that what it conveyed is that these things were not things that were done with a 10-year plan, from start to finish. There was a lot of coincidence, a lot of different ideas. It was important to have different communities. Many of the ideas did not originate in the information theory community, but were either brought to us from the outside or people from the inside brought them into the community. Now, which brings me to the most important part, which are people, okay? I had the fortune of benefiting from an amazing set of people. I could have started in kindergarten, but I didn't want to start there. Okay, let me start in high school, okay? This was my chemistry and biology teacher, itself a researcher, just, found it really, really inspirational. This was at TU in Vienna. In particular, Franz Lavac gave me the chance to work on my first paper in signal processing and kind of instilled with me that perhaps it would be fun to be a researcher. Then I had the great fortune to end up in Washington University, and in particular I have the great fortune to have Bixu as my supervisor, who himself had benefited a lot from Jim Massey and was always available, always encouraging, in particular tried to instill with me how important it is to write things down properly. I cannot claim I was a particularly good student in that respect, but he definitely tried, okay? And so, another set of inspirational teachers. I had also the great fortune that there were several people like Dave Forney and Dick Blayhood, who for various reasons would come there. And since WashU was a small place, you would have you would have access to their brain for many hours. They couldn't run anywhere, okay? And so that was very, very important, okay? And then, some great friends that I'm still in touch with now, Quinn Lee and Fausto Di Biase. Then, if you had asked me at that point, what would I like to do? I definitely would have liked to go to Bell Labs, and somehow by miracle I ended up at Bell Labs. I mean, just look at us. We are so young, right? It's amazing we were allowed to do research without adult supervision, right? I mean, right? But it happened, okay? Not everyone is on this picture. Also, let me sing. Aaron Weiner, right? Just an inspiration in terms of research, but also, you felt with him this infectious enthusiasm. Every day going to office to him is like a kid in the middle of summer finally getting some ice cream, okay? You could see that kind of excitement, right? And that's just infectious. Rajiv Leroy, Gerhard, Alex Schickman, Hani Lander, and just an amazing person around the seminar series. And then, so many amazing people who were, constantly visiting. I just picked out 3 that, perhaps I had the most contact with, all, constantly encouraging, willing to talk to you, giving you advice. Just a most amazing atmosphere. If you want to know how important my stay at Bell Labs was, okay, you just need to look at that picture, okay? With Tom, as soon as I started for many years, we would, for many, many hours per day, just talk, trying to figure things out. Just amazing collaboration. No BS meetings with Excel, whatever, this, that, invites or whatever, calendar invites. Just meet as soon as you arrive, okay? And when you have to leave, well, you have to leave, okay? Just an amazing interaction. Okay, what can we say? How could we possibly adequately describe Alon, okay? It's a question, I don't know, okay? Okay, so, just an inspiration overall. He, always, marches at his own drum, a very distinctive style, never goes after the trend, has been successful in so many ways, in particular, way before it was popular, connecting with the CS theory community, connecting with the machining theory, being successful in both. And, one thing that we also know him, most of you probably just know him as the organizer of ITA. Sorry, okay, just a joke. He showed us that it's possible to organize, one of the most exciting conferences ever, okay, of a size of 500,000–600,000 people, and to do it in real time or past, okay? I have an important service announcement. The poster for 2023 is almost ready, okay? So, great. Emre, again, already at Bell Labs, a few doors over, now next to me at EPFL. He, students put up cardboard cutouts, life-size, in front of our 2 offices. In front of mine is Darth Vader. Fair enough, okay? In front of his is Dumbledore, because we call him Emre the Wise. Okay, you walk in his office because you want some advice on some math problem. You come out 10 hours later, you know everything you didn't even want to know about how to install LaTeX, how to, how to tie a tie, Burgundy wines, opera. He will sing to you the Schöne Müllerin, whatever, okay? Just amazing to have a colleague of you. I wish each of you had an Emre just next door, okay? And I mean, again, it was fantastic to meet him at Bell Labs, then great to have him as a colleague. Now he has done an amazing startup, shows some people know how to do it all. At EPFL, many of you might know Muriel, somehow has managed to keep me out of trouble. Damir, Nicholas, desperately trying to teach me statistical physics and now quantum. Olivier, great to have around, and François Benoit. I already talked about these 2 guys. Michael and Janos Gell, who humor me every time at lunch. Okay, all our conversations start with some exciting news of the day and end up of 10 ways to die. I don't know how this happens. Okay, but that's it. And of course, Emmanuel Abbe. Fantastic to have him around and talk to him about various topics. Christina and Suaz, who were there, but now unfortunately anything. And again, they're not formally part of our group, but they're visiting so often. What's the difference? Okay, fantastic to have them, of course. Shlomo and also Jean Papier. There are lots of colleagues, but there are too many colleagues, so let me just pick one. Okay, it's Martin Vetterli, who has done a lot. Okay, and only cynics would say that. I'm just putting him up because I was the president and he will decide on our budget tomorrow, okay? So it has nothing to do with this, I assure you, okay? Now, of course, what could be more fun to work with students? As you get older, you get more cynical. you lose some of this enthusiasm. You know, what's better to have access to just enthusiastic, amazing, interested people, okay? Now, I learned so much from them, and it was so much fun. You know, I learned, for example, from Abdel, that procrastination is a virtue, okay? I learned from Marco, many other things, but everything is better with balsamic vinegar, okay? Squirrels are super smart, but they're also very, very secretive, I can tell you that. If I ever managed to pull up a prank, it's because I learned from, by far, the best, the master, okay? Jeremy Esri. I learned about competitiveness from Satish Kurada, okay? You can see how happy he is, okay? I learned that my body mass index is highly dependent on the student I'm mostly working with, okay? I learned, that there's an entirely different level of social interactions, okay? I always try to introduce the students to someone, not with Amin, okay? He introduces me to people. Of course, with Hamed, amazing to work with him, but I also it's due to him that I'm the happy recipient of a soccer trophy. And pro tip, if you don't really know how to play soccer, but you still want to have a soccer trophy, join the Iranian team, okay? That always works, okay? Of course, the one and only Srinivas Kudikar, probably one of the longest collaborations, first when he was working together with Nicola Marquez and myself, but since then, interactions, almost every week, sometimes on technical parts, sometimes completely crazy, other ideas, always helpful, always enthusiastic, the one person responsible for a miracle that my slides were already ready on Monday, never happened before, will never happen again. So thanks a lot. And from all that learning, okay, that's how I felt often, okay, completely completely exhausted, okay. That's how much learning I did. Now, still a few other collaborators that on the way that didn't fit in there. I had the great fortune to meet Andrea Montanari, particularly when he was still in Paris, and I could just jump on a train. Again, many years of interactions. It's just really, really enjoyable to learn from someone that has this mastery of statistical physics. Henry, who was a postdoc, a perfect blend to me of an engineer, a mathematician, a physicist, just the perfect package. And Igal, who has just this real scholarly attitude, this real seriousness about him. Again, he was a postdoc, very enjoyable to work with him. That's how you know him. That's how I know Henry. Okay. There's a fantastic picture of Andrea in his yearbook, but I cannot show you. Okay. But you should ask him. I don't think there's any embarrassing picture of Igal. Okay. And then, of course, colleagues in coding. I stole this picture from Costello. Probably should be updated, but just look at that, right? Fano and Viterbi and Burlicam and whatever, right? I had the great fortune. I didn't meet all of these people, but many of them I had access to people. All of them extremely helpful. Not a single one where I would say, okay, great. All of them really, really nice. Okay, this brings me to the final thing, family. Okay. Somewhere in there must be my mom out here. No, it's not. I don't know. I don't see her, but doesn't matter, okay? I learned from my dad, I think, passion for tinkering with mechanical things. From my mom, probably a passion for just figuring things out, and probably also my stubbornness, okay? And from my sister, she got all the artistic talent, so not much left for me, but I was fortunate because she did all the stupid things kids do 2 years ahead of me. So when I did them, nobody blinked an eye, okay? And I basically was brought up like a free-range child. Nobody ever knew where I was. Really, really fantastic, okay? And then last but not least, always look at the sunny side of life. And, they are said that married men live longer, okay? I'm counting on a more specific correlate. It says men who are married to cute, funny, considerate, amazingly smart French girls live the longest. Thank you very much. Okay.
Thank you, Rudy. So unfortunately, before we field questions, you're not quite done yet. I think keeping in tradition with your decompression event at ITA and in the tradition of Shannon, who was not just a fantastic information theorist, he was also a juggler.
Uh-oh.
I thought maybe you could entertain us a little bit. So I brought a few juggling balls here.
That's very kind of you.
Of course. And so, why don't you show us? I mean, I think a Shannon Award.
I'm sure in my mind I'm great, but I don't know.
Well, it's not just about the capacity; it's about the algorithm. Oh, come on. Okay, I mean, let me help you a little bit, right? I mean, what did you say in your talk, right? I mean, wonder a bit, borrow, adapt, and repeat. So let me see. Take it up, launch it, dump it. All right. All right. Here we go. Wonder, borrow, adapt, and repeat. Urbanke. All right. Thanks again for this amazing, inspirational talk. We have time for a few questions. All right. Erdal.
I thank you, Rudiger. Congratulations, and thank you for this very entertaining talk. So what do you see looking into the future? Do you think we are close to the end of the road, or do you anticipate some further major breakthroughs in coding?
So, I guess in the 60s they had this motto, never trust anyone above 30. And I think in research should be never trust anyone above 50 to tell you about the future, okay? But I have no idea what's ahead. But all I've seen is that even though information view encoding has been set dead 4 or 5 times, right? And every single time something happened, right? A new technology came along, a new application came along, something. And very often it's happened when people looked at something that was completely well established, everyone understood it, but they understood that there was an assumption in there that perhaps was no longer valid, right? I remember at Bell Labs, there was GMASO. Bell Labs was important in the early development of the modem. This was the modem that was analog, right? And GMASO gave a presentation in front of the board, and then someone on the board said, well, but that's no longer the actual model in the channel. It's now digital inside. You can have accesses, and that gave rise to V32, a lot of flurry. So I'm sure something new will happen. The obvious thing is now quantum, right? It's kind of sad to see that we are not more, as a community, not more present in the development of quantum codes, right? It's an obvious thing. Maybe it's not such a big commercial thing right now, but it's a great scientific challenge, and I would love to see, it's not like nothing is happening. Some papers, Calderbank, for example, recently, I think Henry also had something, but right now, a lot of the, I think, very interesting things are driven, for example, by theoretical computer scientists, right? Why them? Why not us?
So I wanted to ask a little bit about, so many of the methods from statistical physics, fixed point equations kind of things, are very general. Do you see some of these same methods playing maybe a bigger role in machine learning, in the analysis of machine learning systems? Because I think in many cases, maybe it's already happening, but maybe you could talk a little bit about your opinion on that.
Yeah, I think there's some papers. Of course, I thought about it because it's the obvious. But you have to probably think about it in the right way. I think many of the mean field methods, like nder, for example, has been quite successful in looking at that, right? Looking at mean field methods, Nicola Macris, for example, looking at that, right? It's typically for one hidden layer neural networks where these methods work. So yes, clearly some of these methods will play a role. In general, still, of course, right? If you look at the development, it's such a gold rush right now that is really driven a lot right now, unfortunately, not unfortunately, but by applications, right? So theory is like often still lagging behind, but I think the theory that happens is very much motivated by statistical physics, right? Or physics in general.
Any other questions? Yes, yeah, we're getting a mic.
Congratulations for Shannon Award. Appreciate your wonderful presentation. As you know, Polar code and FDPC code was adopted in 5G for control channel and data channel. I think now it's time to look forward to 6G. So will you please share your point on the channel coding for 6G? Thank you.
Let the best one win. You know, I think it's exciting to have, you know, competition what drives us, and so I think it's exciting that there are different teams working on different areas. Who knows who will win at the end? I mean, particularly, you know, we are talking about this theory part and so on, but in standards, you know, there have to be whatever 1,000 different rates and, you know, memory requirements and so on. That's much more complicated, right? So I think it's exciting, and the more, you know, applications there are, the more the competitions are, the more grants we can write and the more papers we can do. Amazing, fantastic, okay? So I don't know what will happen, okay? And who knows, maybe someone entirely different, okay? Maybe young Erdal will come around, okay, and give us something entirely different all together.
Okay, thanks.
Maybe. Yeah, Rodiger, maybe.
Go ahead, Shlomo.
About the question here. Information theory, what do we know? Channel point-to-point, we know nothing. What about networks? What do we know? The multiple access channel? Where are the rest? Broadcast channel, the relay channel. Actually, we know nothing. It's that we are at the start, not at the end. And in fact, maybe methods of statistical physics, as we heard from Amir Dembo, maybe they can be used to show converses. Like the Marton region. Maybe it's tight, huh? So we are at the start.
That's the spirit. We're at the start. We're at the start. Okay.
Yeah, more than a question, I would like to thank you and your collaborators, Erdal, and all these other amazing coding theorists, because when I started doing research as a PhD student, I remember that, so I'm, of course, as many in this room, more like communication oriented. And every time I used mutual information and say, well, okay. And there was always a reviewer saying, well, mutual information capacity is not really HGO, you should use a cutoff rate or something like that, right? But thanks to your work, now in communication papers, we use plain and simple mutual information, and this is unarguable the right thing to do. So,
or the cutoff rate.
well, so it's very good that thanks to the fact that these things have, you know, this limit can be achieved. Now also the analysis of systems is simplified. Just look at you know, at performances in terms of mutual information, and there will be always a Rüdiger Urbanke filling in right code to get very close to that. So thank you very much.
All right. Let's try to keep on schedule. I've already derailed enough sessions, I think. So let's have a big round of applause for Rüdiger Urbanke.
Exactly. Thanks. Very nice.
All right, that concludes our plenary lecture and channel lecture for 2023. I want to remind all of you that we have an event with Rudy later today, meet the Shannon lecturer. I encourage many of you to go and attend if you want to learn more about Rudy. These events are usually super fun, very entertaining, so please attend. Thank you very much.